Hello everyone, and welcome to this lecture series on the Holt-Winters method. In this particular lecture, we'll worry more about the equations and the overall theory behind the Holt-Winters methods, and in the next lecture, we'll show you how to use stats models to code them out. So previously, we just saw with exponentially weighted moving averages, or EWMA, we applied simple exponential smoothing using just one smoothing factor, which we called alpha. However, this failed to account for other contributing factors like overall trend and seasonality. So if a simple exponential smoothing, we only have one parameter that we can factor in. As a quick note, before we move on and discuss Holt-Winters and how it's better than exponentially weighted moving average or able to take in things like trend and seasonality into account, I want to just clarify we're not going to be using Holt-Winters method for forecasting just yet. However, in the next section of the course, when we talk about an introduction to forecasting, we're going to reintroduce Holt-Winters and actually use it to forecast on future data that we don't already know. So right now, all we're doing is we're going to learn about Holt-Winters methods, such as double exponential smoothing and triple exponential smoothing, and then we're focusing on fitting that Holt-Winters models to an underlying time series dataset that we already know all the values for. We're not going to be doing forecasting with Holt-Winters just yet. That's coming in the next section. So hold on to your horses for just a little while longer, and we'll be able to use all of this and more with forecasting in the very next section of the course. But for right now, let's learn about the theory of Holt-Winters methods, how it can be applied to data sets, and then we'll learn how to forecast in the next section. So in 1957, Holt, who was studying economics, came up with a double exponential smoothing method, and then later on in 1960, Winters extended that to actually capture seasonality. So because the work is very closely related, often these set of methods are called the Holt-Winters method. So essentially, the Holt-Winters seasonal method comprises of the forecast equation and then three additional smoothing equations. So these three additional smoothing equations, one of them is called for the level, which we label L sub t. The second one is for the trend component, which we call B sub t. And then the third one is for the seasonal component, which we call S sub t. And each of these different equations is going to have a corresponding smoothing parameter, alpha, beta, and gamma. Now keep in mind there's two variations to this method that differ in the nature of the seasonal component. And this is going to feel pretty familiar from our ETS decomposition discussion. So for that seasonal component, there's two main methods when we're talking about the Holt-Winters seasonal methods. And the first method is called the additive method. And the additive method is preferred when the seasonal variations are roughly constant throughout the series, while the multiplicative method is preferred when the seasonal variations are actually changing proportional to the level of the series. Okay, so we understand now that there's kind of two flavors here depending on that seasonality term, additive and multiplicative. So let's explore now the overall buildup for the Holt-Winters methods, which allow us to add on double and triple exponential smoothing. But first, we can imagine we have a base method that we call single exponential smoothing. And this is essentially what we just did with pandas with exponentially weighted moving averages. What we do is we have y naught equal to x naught, and then we specify that our model is going to model y at some time t is equal to 1 minus this alpha term at yt minus 1 plus alpha times the value at xt. Now we can expand on this to double exponential smoothing, and this is otherwise known as Holt's method. And here what we're going to introduce a new smoothing factor called beta that addresses the trend component. So this is Holt's method for the trend component, and this is called double exponential smoothing. And what ends up happening is we have this system of equations here, where we have LT for the level at time t, which we define using an alpha parameter. We have B sub t, which we end up using to define the general trend, and then we relate these two as LT plus BT is equal to YT. And then we can use that to predict some period ahead, which we call plus H. So let's break this down, and the equation gets a little smaller here, but here we've labeled everything. We have now these two separate components of the fitted model. So we're going to say that our model, y sub t, so the actual value of y at any given time t, is going to be equal to LT plus BT, which basically indicates that we have this level component plus some trend component. And right now, we're actually not taking into account a seasonal component. So this is just Holt's method, and the reason it's double exponential smoothing is because we're no longer dealing with just an alpha parameter in the level component, but now we've introduced a beta parameter for the trend component. And so then our forecasting model, which we're not going to use quite yet, but we will in a future section of the course, would then just be defined as yt at some predicted point in the future, that is h, some number of periods into the future, would just be lt plus h times bt, that trend. Okay, so we can kind of get the idea here, at least in theory, that Holt's idea is that he's separating out the time series data into two main components, the actual level or value component and then the trend component. Now, because we haven't yet considered seasonal fluctuations, the forecasting model is essentially just a simple straight sloped line extending from the most recent data point. Because if we take a look again here, we're really just considering the value at level and then the trend, whether it's sloping upwards or downwards. We're not yet taking into account some triple exponential smoothing, which would be able to account for seasonality. All we're able to do here is just predict a general trend upwards or downwards or flat. Now that trend should be able to match up pretty well to the historical data. So to give you an example of this, if we think back to that airline passengers data set, if we were to use Holt's method, just double exponential smoothing, it would be able to predict that airline passengers are increasing. What it wouldn't be able to predict then is that they increase more rapidly during the summer than during the winter. So it would just be able to predict the general level and trend of that data series. But luckily we have Holt-Winters method, which is the Winters add-on to this, which is known as triple exponential smoothing. So with triple exponential smoothing, otherwise known as the Holt-Winters method, we're going to introduce a smoothing factor called gamma that addresses these changes due to seasonality. So now we're basically adding in one more component here called C sub t, and now that stands for our seasonal component, and that has its own factor, which is gamma. So now we have these three different components, which we have the level component, LT, the trend component, BT, and then the seasonality component, CT, each with their own specific factor, alpha, beta, and gamma. And then YT is going to be equal to LT plus BT multiplied by that seasonality factor. Now, as you may have noticed, there's actually a capital L introduced to the forecasting model. So here that capital L represents the number of divisions per cycle. So in our case, if we're looking at monthly data, such as that passengers data, that displays a repeating pattern each year, we would say that L is equal to 12, the number of divisions per cycle. So again, now we've actually defined our fitted model as having three subcomponents: level, trend, and seasonal. Now, don't worry too much about having to write out these equations by hand and then plugging in to figure out what should alpha be, beta be, and gamma be. Really, that's what stats models is going to be doing for us. What you should be focusing on as a user of stats models and trying to use these to understand the model that will fit your time series is just that you have the Holt-Winters method, which only had the level and trend component. So that would predict a kind of straight line shooting off of your last time point. However, with the Holt-Winters method, this triple exponential smoothing factor, we now are able to take into account that seasonality component. So now we're defining our fitted model as a subset of these three components: level, trend, and seasonal. And then we can also then build a forecasting model off of this using this kind of semi-complex equation where we're using this capital L as a representative of the number of divisions per cycle, because that's the way the math works out due to the way Winters built out that seasonal component. All right, so coming up next, let's go ahead and explore how we can actually use stats models to build out Holt-Winters method and build a model that will fit a current time series. Keep in mind, we're not actually going to be using that bottom forecasting model equation that's coming up in the next section. Right now, we're going to see how we can apply the Holt method and then the Holt-Winters method to build underlying models to data that we already know about. This should be pretty exciting for you, especially when you see just how well it can fit the data with kind of these simplistic ideas of triple exponential smoothing. All right, let's get started. I'll see you in the next lecture.